Okay, so we'll start integration today. So I did in the last class I discussed about interpolation, and we'll use Lagrange interpolation in today's lecture as well. Okay, so there is a connection. I mean, Lagrange interpolation, I think I told you that is a mother of not all, but let's say many numerical algorithms, and you'll encounter it today. Okay, so we will cover two methods in the class. One is Newton-Cotes and second one is Gauss quadrature. So Newton-Cotes is simpler compared to Gauss quadrature, and that is the topic of today's lecture. And needless to say that integration is a very critical thing. No? I mean, we encounter integration all the time. You need to sum up a function for large data set, then that's the integral. Okay. In physics, we have integral all the time. We want to compute, like in quantum mechanics, the average property of something, integrate. So we need it all the time. Okay, so numerical integration involves only finite set of points, and not we don't have the full function. The idea is that we really don't know the full function fx, but you approximate the full function by, in fact, Lagrange interpolation at some discrete points, and the values of the function at these discrete points are this fxi, but we need to multiply that by weight. So I want this integral to be as close as possible to the real value. So we want this integral to be as close as possible to real value. So our objective is to get the weights. Okay, these are called weights, and this xi is called abscissa. So you need to choose. So the interval is a to b. We need to choose points on which I will evaluate the function fx, or I will have the values of the function is given to me as a data. So this is fxi. My handwriting is not so great, but this fxi, so this function are not delta fxi. So at all these values, including a and b, so we have these values. So well, sometimes we may not need a and b, but well, sometimes required. So and weight. So the simplest method, which is Newton-Cotes, abscissas are chosen by you, by the user, but weights are to be computed for those abscissas. Okay, wi's. But for Gauss quadrature, which I will do in the next lecture, we can fix both. Abscissas also not given to you. I mean, you don't choose abscissas. It is chosen. Well, I would say that abscissas are not arbitrary. They are chosen to optimize the integral. So the two methods, one simple method is xi's are chosen by yourself, is your choice. Now for today's lecture, we'll assume equidistant xi's and determine wi's. Okay, this is called simple method. But the more complex method is determine both xi and wi for minimal errors. The Newton-Cotes is the type 1 simple method. So I hope this part is clear. What is the motivation? So please remember that we don't know the function, but we know the values of the function at only discrete points, not everywhere. Okay. So some notation. We have n points. So please remember I have n points and m interval. So this will be used throughout my lecture. So m intervals. Okay. So you can see here how many points? There's 7 points, 7 blue dots, and 6 intervals. You can 1, 2, 3, 4, 5, 6, and the distance between two neighboring neighbors is h. Is assumed to be uniform for today's lecture. Okay, we assume uniform spacing h. Okay, so m is the number of intervals, n is the number of points, and b minus a is mh. Okay. Now, remember, through n points, we can pass a polynomial. This is a Lagrange polynomial. Okay, this I did in the last class. Okay, so here I have this Li is a Lagrange interpolating functions, polynomials, in fact, and this is the value of the function. Okay. In the last class, where I used to use Ya as a notation, but in today's class, I'll use F or Yj. So we'll use Fxj. Okay. So in fact, you'll use this Pn as an approximation for Fx. So Fx I don't know, but I say, well, given endpoints, I'm going to approximate Fx as Pn. Okay. So let's do next. So this is what I wrote. So I'm interested in computing the integral a to b. This b is missing here. Fx dx. So since Fx is approximated by Pn, so I say, well, Pn x, I integrate a to b. Okay. Now, remember, Pn is approximated by this function. Or rather, not Pn. Pn is that function. Fx is approximated. Pn is this Lagrange interpolating function multiplied by yj's or fxj's. So fxj is a constant, so you'll come out of the integral, and what we'll get these guys, Ljx dx, and I need to sum for all the data points 0 to n minus 1. Okay, so that's where we need to sum this up. So we write this as look, dx is proportional to h, or dx in fact is h. So the integral will be proportional to h. Okay, h is a parameter in fact. So h is coming out, and we write this as sum j equal to 0 to m. Okay, cjm fxj. So m is n minus 1. So please remember. So this for all the intervals. So that is that. No, sorry, interval plus 1. All the points. Okay. Now this coefficient is there, CJM. Okay. So this is the coefficient I need to give you, or you need to compute. But it has already been done. I mean, you don't need to compute. It is there in the tables. In fact, Python has it in this library. Now CJM. In fact, what is weight? Wj. Wj is nothing but h times CJM. Okay. Remember the definition is this integral is sum Wj fxj. That is the sum. J 0 to n minus 1. Okay. So that is Wj. So once somebody gives me CJM, I know Wj. And or we can write down this CJM as well. I mean, this is coming from the definition. Integral by h. Okay. So that's CJM. Now, CJM satisfies certain properties. One important property is that this one, CJM, if I sum over all the points, then I get M. Okay, how do I prove it? Straightforward. Take fx equal to 1. Okay, so what is the left hand side? It is b minus a, right? This is a constant, this is b minus a. Constant function, so integral of constant function is just b minus a. Now, right hand side will be fxj is 1, so it is going to be h times CJM. So h times sum CJM. But h is nothing but b minus a by m. So b minus a cancels, and you get this equals b minus a. So cancels. So I get CJM. Sum is m. Okay. So you can verify. If you're doing it yourself, then you should make sure that this identity is satisfied. Okay, so this is the crux of today's lecture, that we approximate function fx by a polynomial, a Lagrange polynomial in fact, and we integrate it, and that integral will be of this form, okay, this form, and it has this weight, which is this one, and fxc. So CJM will be given, in fact, you can compute it yourself, but package of Python, and we can just get this. Now basically I will talk more about this idea. Let's do a simple function just to get used to this idea. So we have 2 points, n equal to 2. So these 2 points are here and here. Okay. Now my function is a black curve. Okay, so this is a function, black curve. Now with 2 points, what is Lagrange polynomial? It's a straight line, right? I mean, we did this in the last class. So this is the Lagrange polynomial, straight line. So if I just do the so this is a Lagrange polynomial, and integral will be, you can just integrate this function. This you can just do it yourself, and it's going to be h by 2 fa plus fb. So this is h. So it's average of the left point and right point multiplied by h. Now it looks like trapezoid, no? This in fact this value is this area, the blue area. Okay, that is why this is called trapezoid rule or trapezoid method. Now remember the function is this black curve, which black has become a yellow curve. So what is error? Error is at region A. Okay, that's error. I'm estimating the area under the curve or the blue region. So the gap is the error. Okay, so if the function is linear, then I get exact value for the integral. But if the function is not linear, then there will be an error, and that is A. And we'll see later how to evaluate A. Estimate A actually. You can evaluate it for some cases, but you can make an estimate. Okay, and so C01, C02, I mean, you can see that is half, right? Now we can go to slightly more complicated function. So not function, more procedure. We take 3 points, n equal to 3. So 3 points will be here, here, and here. Okay. Now we can do the. I mean, now I'm not doing the algebra, but you can do it yourself. You can use P2, P3. Sorry, P3. P3 is a Lagrange polynomial with 3 points. P3x. Integrate this, and answer is this. Okay. So h by 3 fa plus 4 times the value of the function in the midpoint here, and this one. Okay, so if you can see that, and the endpoint. Okay, so these are the endpoints, and the endpoints, and the midpoint. Okay. Now, if the function, so I'll just state it. I mean, we can prove it a bit later. If the function is quadratic, that means the highest order of the polynomial is x squared. Okay, so if the function is of this form, if f of x is like this, then this gives you exact integral. Okay, it turns out you can in fact easily see that, but it turns out if I add a d cube in that, dx cube, sorry, not dx cube, then also it is exact. For cubic functions or polynomials of order 3, also this function is exact. And why it happens like that is because this function, this one has this structure like this. In fact, it has, I'm kind of this schematic. It turns out that at some places the function is above this. By the way, this integral is nothing but area of the blue region. Okay, you can prove it. This one is basically the area of the blue region. The quadratic polynomial is going through it. That is P3x, and the area is that blue region. If it is quadratic, then I have exact. If it is not quadratic, if f of x is cubic, then sometimes I have overshoot. The function is above the blue region and below blue region. So this function b and c are equal for this function, cubic order, and so b and c cancel. So with P3x, I can get a pretty accurate integral for cubic polynomial as well. Okay, the proof will follow. Okay, just give me some more time. Now we can do it for 4 points and 5 points and so on. So this is m, a number of intervals. So n will be just add one. So this is 2, 3, 4, 5, 6. So with the 3 points, we had this 4/3 rule. So 1/3, 4/3, 1/3. I showed you in the last slide. With 4 points, we have these things, these 4 values. Okay, and so these two are called Simpson rule. No? Simpson's And as I said earlier, this is called trapezoid. Okay, others ones have some names which I don't remember, but I don't know. But anyway, so you need to remember these two names. Okay, with 5 points, we'll have 5 weights: 1, 2, 3, 4, 5. And I don't remember. In fact, I only remember the first one, trapezoid. With some labor, 1/3, 4/3, 1/3 is easy to remember, but the rest all I don't. And you can see in the table. Now, so in fact, you don't even need the table. Like Python has it in a library called, or package called scipy.integrate. Okay. Now, from that, you import Newton-Cotes. So please remember scipy.integrate.Newton-Cotes. That's our module. So I import this. Now I have m intervals. By the way, for historical reasons, number of points is not is not the parameter for these functions. Number of intervals are. Okay. So when you use it, please make sure that you're giving intervals as a parameter for these functions. Now m is that interval, f is the function. Okay. And a, b are the limits. Okay. So I want to integrate using Newton-Cotes. So we have x is I make linspace. I mean with m plus 1 points. M plus 1 point, a to b with m plus 1 points. Now call Newton-Cotes. This function Newton-Cotes, and it has m is a parameter, m interval, and I put comma 1. 1 is for equispace point. Okay, so don't worry. So you, for this course, please use 1. Okay, as a parameter. Now it gives you two values: coefficient and error. Okay. In fact, it's going to give you. So this will be a list, a number. I mean, this will be a set of numbers. And so this will be one number. Actually. This error will be one number, but coefficient will be a list. So these are weight space. Well, not CIJs. Not weight. Weight has factor. So this CJM. Sorry, CJM. So this is coefficient. Okay. Now I compute H, which is B minus A by M. Okay. So what is the value of the interval? H star sum of coefficient and fx. So fx is the value of the function at different points. In fact, all these points. So this is also is function, but basically I have a function at discrete points, not all the points. So discrete points are this function. So this is m values, and sorry, not n values, m plus 1 value, and coefficient is also n values, m plus 1 value. I just do the sum. So this is my integral. No? This is the formula of this integral, and okay, this is a function right now. But okay. Now I want to evaluate x4 integral x. So this is integral 0 to 1, x4 dx. Okay. Now I'm using m equal to 4. So I use 5 points basically. So what is it going to do? I mean, when I call this function, this lambda function is a lambda function. Okay, so it's going to be evaluated at those 4 points and will be plug in there. F, or not 4 points, 5 points. Okay, you just go in there. So the function which I'm giving there. Actually, no, I take back. So this function is calculated here, fx. Okay, so I am giving a function here. I'm giving a function. I'm not giving a list. I'm giving a function, full function. So this function is evaluated here. There's evaluation of function. Okay. So I have m equal to 4, which is 5 points, function, and the intervals 0 and 1. And what is the integral? If I just do this, I mean, this program is obvious. If I do this, I'll get answer as 0.2. In fact, it's the exact value, 1/5. Now, why do I get exact values? Okay, I'll give the answer, which I'll prove it in a couple of slides later. So with 4 points, I can get with 5 points, I can get exact integral for any polynomial of order 4. Okay, with 5 points, in fact, it's odd number point. So any polynomial order 5. With 5 odd points, we can get any order of the polynomial with that number of points. Okay, so this will be exact. So one important remark I would like to make here is that numerical integration doesn't mean that you will have errors always. There are occasions when we get exact results. You just find those algorithms which give you exact results. Okay, is as good as mathematics. I mean, exact integrals you want, you will get exact integrals. Okay, only problem could be the round off errors. Okay, but other than that is exact. Now, if I use m equal to 2, that means 3 points, then I don't get 0.2, but I get error which is 0.008. Okay, it is less than 1%. It's just 3 points. Okay. Now, with m equal to 3, that is 4 points, I also get error. But okay, so the error is here 0.003. But with 4 points, with m equal to 5, which is 5 points, I get exact values.